Hello, welcome to our video about polygons, its features, and how we mark them. We want you to take a look at this collection of shapes right here. What do you notice and what do you wonder about these shapes? In math, we have a term called polygons. Which of these do you think are polygons? This is a polygon, this is a polygon, this is also a polygon, this shape right here is a polygon, and this one right here is considered a polygon. Alright, based off of what we circled, what do you think a polygon is? We're going to look at our examples of polygons and non-examples to see if we can come up with a definition. Alright, let's look at one that wasn't circled. Let's look at this one here. We notice that this has a curved edge. This also has a curved edge, and all the ones that are circled do not have a curved edge. So one of the qualifications of a polygon is that it has to have no curved edges, only straight edges. Let's take a look at this one. This one was also not a polygon. Well, we see that the other ones here that we did circle that are polygons are all enclosed. This one, right, it goes and then it doesn't close back on itself. So in order to be a polygon, it has to be closed. Let's further refine what enclosed means. Someone could go here and say, oh, that's enclosed. And yes, that would be a polygon because all the edges meet up. What if someone tried to do it like this? They go down here and then through and then meet back up. Okay, all the edges technically do meet up. However, this crosses over itself. So no edges can cross over itself as well. That's also part of the definition. All right, so now we have a definition for polygons. It's any shape where there's no curved edges, it is enclosed, and none of the edges cross over itself. We're gonna look at a couple of these polygons and learn how to name and notate them. We got a couple polygons hold up right here. Polygons are made up of vertices and edges. A vertex, which is just a single one, is just the points. So we have all the vertices highlighted for you guys here. Again, vertex is a point on any polygon. Sometimes it's helpful to refer to certain parts of the polygon, so we like to name vertices with capital letters. So I can name this vertex capital A and just kind of go around. This is a separate polygon, so I'll probably name it with separate letters. All right, now that we talked about vertices, let's talk about edges. Edges are the line segment created between two vertices. All right, so we have a couple edges highlighted for you here. I would name this line segment AE. Sometimes it is written with a line segment bar above to let you know it is a line segment. I could also refer to this line segment as EA. It does not matter because this is what we call the reflexive property. AE is the same thing as EA because I could go in either direction and it works. Looking at this line segment, we would call this line segment XY, or we could also call it YX. Okay, you might see it with a line segment or without. Either way works. Now that we've talked about edges, let's talk about how to name angles. Angles are the space between two adjoining edges. This is the space between edge AE and edge DE. I can refer to this as angle AED because that's the way I'm reading it, AED, and that is the angle that is included between line segments AE and ED. Or I could also go the other way using the reflexive property DEA, or even simpler, I could just refer to it as angle E. On Derivata, you'll often see it written in the 3-letter format. Let's name an angle on this one. If your Derivata assignment asks you to name the angle that is included between XZ and ZY, then I know that it's talking about this angle right here. That is the angle adjoining this edge and this edge. So I would name this angle XZY, or I could also go YZX. The order doesn't matter using the reflexive property as long as Z is still in the middle, since that is the angle that is included between the two edges.
We have two new polygons put up here on the screen, and we can check to make sure that these are polygons. So they have no curved edges, they do not cross each other, and they are both enclosed. So we know that these are in fact polygons. So I have labeled the vertices of this polygon A, B, C, D, E, F, and then we have an exact copy of this same polygon right here. But I don't want to label this A, B, C, D, E, E, F on this polygon as well because that won't be able to distinguish between the two. So instead, I'm going to label this one G, H, I, J, K, L because these are two separate shapes, even though they are congruent. That is a word that we need to know. Congruent means that they are copies of each other. They have the same angles, same shape, same side lengths. Everything's the same about them, but they are just copies of each other. In math terms, we are going to write this as polygon A, B, C, D, E, F, and we said that it is congruent to this shape, right? And the congruent symbol looks like an equal sign with a little squiggly on top. So A, B, C, D, E, F is congruent to G, H, I, J, K, L. So if I look at vertex A on this polygon right here, which vertex do you think vertex A corresponds to in polygon number 2? Well, A corresponds to G, because if I were to take this shape and slide it down, polygon, A would match up with G, B would match up with H, C would match up with I, and so on. If we didn't even have the pictures of these shapes and we only had this statement right here, because of this congruent symbol, we could see that A is congruent to G, B is congruent to H, C is congruent to I, and so forth. So just like angles correspond to each other in congruent shapes, the edges or the side lengths also correspond. So if we're looking at side length DE in our picture, we can see that it corresponds to JK. But we can also see it in our congruent statement right here. If we find side DE, we can see, oh, well, that corresponds here to JK. Or if we wanted to look at AB, we can see that that corresponds to GH, and we can see it corresponds to GH right here in our picture as well. So if we know that two shapes or two polygons are congruent, then we know that the parts of each polygon are also congruent to each other. So the angles of this first polygon are congruent to the angles of this polygon. The side lengths of this first polygon are congruent to the side lengths of this polygon. So we can say that corresponding parts of congruent polygons are congruent.
Let's talk about some other features of polygons. We can talk about symmetry. If a polygon has reflection symmetry, you guys might be familiar with this. It means that I can draw a line of reflection either up and down, or I could draw a line of reflection here, and the polygon will fold onto itself. So if a shape has reflection symmetry, it means I can draw a line of reflection where the shape can fold onto itself evenly, or you can also think mirrored. This pentagon here, it looks like it has 5 lines of reflection, because I can draw 5 lines of symmetry for it to fold onto itself. Let's take a look at this triangle here. I know I can fold it this way, and that would be a line of reflection. I don't think I can go this way, because if I did try going this way, it doesn't quite match up. It's a little off from each other. All right, another way that polygons can be symmetrical is through rotation symmetry. If a polygon has rotation symmetry, it means I can take the shape, and after some partial turn, it looks the same way it does right side up. So any shape, obviously, if you turn it 360 degrees all the way around, right, will look the same as it did right side up. But rotation symmetry, the key is that it has to look the same as it did right side up after some partial turn. So I turn this only a quarter turn and it lands on itself. Turn it a quarter turn, it lands on itself. I turn another quarter turn and it lands on itself. So this has rotation symmetry. Let's take a look at what's happening with rotation symmetry with the vertices when they're labeled. So we have pentagon A, B, C, D, E here, and I have another pentagon traced. And you can do this at home. You can trace it on your screen, and then you can rotate it to see if it matches up with itself if you have a hard time visualizing it. So I have pentagon A, B, C, D, E here, and if I rotate it, after some partial turn, oh look, it lands back with itself. So B is now where B used to be here, now it matches up with A. A got rotated here, E here, D, and so forth, right? So notice, although the vertices don't match up in that way, they still create the shape of the original. All right, let's check out this one. We got triangle XYZ here, and if I rotate this at any point, does it land on top of itself? Oh, that's close. Not quite. Not quite. Okay, looks like it doesn't land back on top of itself until we go the full 360 degrees. So we would say this triangle does not have rotation symmetry, but this pentagon and this polygon does have rotation symmetry. Now that we talked about whether a shape has rotation symmetry or not, let's refine it a little bit more and talk about degrees of rotation. Degrees of rotation helps us know how many degrees do I need to turn a shape before it lands on top of itself. So in this case, I only need to turn it a fourth of the way, a fourth of the way, a fourth of the way. So how many degrees does it take for me to get from this arrow until it lands at this arrow? A shortcut, if I don't know that this is a 90-degree turn, is that since a full rotation is 360 degrees, I can just take 360 degrees and I can divide it by how many times I can turn it where it lands on itself until I'm upright again. So 360 degrees divided by the number of turns it takes. In this case, it is 4. I can turn it 4 times before it's right side up again. And that tells me my degrees of rotation here is 90 degrees. All right, let's try it again with the pentagon. I can rotate it once, twice, it lands back on itself, 3, 4, and 5 until it lands right. A is matched up with A again. So I can take 360 degrees and divide it by 5 gives us 72 degrees. So that tells me my degree of rotation for this pentagon is 72 degrees. On your derivative assignment, it will ask you what is the smallest fraction of a full turn that the shape needs to turn in order for it to look the very same as it started. In this case, since I only had to turn it a fourth of the way, a quarter turn, that is 1/4. That would be the smallest fraction I need in order for it to land on itself. Looking at this pentagon here, the smallest turn I need to make it is a fifth of a turn, because there are 5 ways I can turn it before it lands back at itself.
So now that we have talked about features of polygons, let's talk about how we mark polygons. If you look at this trapezoid right here, there's a lot of different markings going on. Each of these markings tells us something about the polygon. So let's start with the angle markings. If we look at these two angles right here, these two angles are adjacent, and that just means that they lie on the same line. If you notice, both of these angles have one tick mark through them. And this tells us that these two angles are the same, or they are congruent. And then if we come up to these angles up here, this is another pair of adjacent angles, and they both have two tick marks. So this tells us that these two angles are congruent to each other, but not congruent to the ones that are opposite of each other. So when two angles have the same number of tick marks on them, they are congruent. Now let's look at the sides. The sides are measured in the same way. Because these two side lengths have just one tick mark, that tells us that they are congruent to each other. This side right here doesn't have any, and neither does this top side. And so that tells us that they are not congruent to any of the sides. The last marking that we want to talk about is this arrow right here. This arrow does not mean that the lines are congruent, because as you can see, this line is much shorter than this line, but they both have an arrow. The arrows tell us that the lines are parallel. And if you remember, parallel lines are two lines that will never intersect each other. And so this tells us that this line and this line are parallel to each other. All right, now we're going to take a look at this rectangle right here and try to figure out what these markings mean using what we learned over here and maybe adding some new definitions. So from what we have over here, I can see that we have a parallel line marking. We have two of them actually. So we have one right here. So it tells us that these two lines are parallel because there's only one arrow on these two lines. And then we come over to these two lines, and they have two arrows. And so this still means parallel, but it just lets us know that these two lines are parallel to each other, and then these two lines are parallel to each other. And then we'll come over to our side markings. We see here that this side has one tick mark, and this side has one tick mark. So these two sides must be the same length. And then the top and the bottom have two tick marks. So this tells us that they are congruent to each other. All right, and there is one more marking on this rectangle that we haven't talked about yet, and that is this box in each corner of this rectangle. And so when there is a box in the corner or the angle spot instead of a tick mark, it tells us that it is a 90-degree angle or a right angle. And so each of these angles are 90 degrees, and so each of these angles are congruent to each other. So now we're given this parallelogram along with the description, and so we have to decide how we are going to mark it using these markings. The first one says that there are two pairs of parallel sides. So that means that two of the side lengths will be parallel to each other, and then the other two will be parallel to each other. The top and the bottom are parallel to each other, so we can label those with our arrows. So that tells us that these two are parallel. And then we also know that these two are parallel. So we'll label those with our double arrows so that we know that this side is not parallel with this side, but it's parallel with this side, and same with these ones. The next description that we're given is that opposite sides have the same length. So we're going to come over to our congruent sides, and we can see we mark them with tick marks. So we know that the opposite sides, so this side and this side, are going to be congruent to each other. So we can label that with one tick mark. So these tick marks tell us that these two sides are congruent to each other. And then we know that the other set of opposite sides are congruent to each other, and we will label them with two tick marks to distinguish between the other set of congruent sides. All right, and then we come to the last one that says opposite angles are the same size. So we'll come over to how we label the angles, and we can see that congruent angles have the same number of tick marks. So if opposite angles are congruent, means that these opposite angles will be the same size. So we will label them with one tick mark, and then these opposite angles will also be the same size. So we will label these ones with two tick marks.
All right, in this example, we're giving an image and we want to come up with the description. So right off the bat, I notice that this is a triangle and it has three edges. So that is my first feature. It has three edges and three vertices. We see that our sides are marked and we have a different number of tick marks for each of them. So this is not congruent with either of those sides because there's not another side that has just one tick mark. This is not congruent to this one or this one, so we can say that all three sides are different. So here we're given a description and we want to mark it up. We see that it has 6 sides. Awesome. It's already drawn for us. All sides of equal length. Since all the sides are equal length, that means that they are congruent. And so I want to mark them all with the same number of tick marks. So I'm just going to pick one. You could do them all with 2 tick marks or all with 3, just as long as they all have the same number. All sides of equal length. Check. All right, all angles are the same size. Let's look at our congruent angles here. And we know that this is the same size as this. Now that we've marked all the angles, to show that they are congruent, we want to add just one tick mark in each of them to show that these are all congruent with each other. If you ever see the word regular, regular means that all the sides are the same length and that all the angles are the same size. So I can have a regular pentagon, regular hexagon, squares are all regular. You can have an equilateral triangle that's considered regular because all 3 sides are the same and all angles are the same. So that's just a special vocab word, regular.